Again, yeah, still tired. Let's do another problem, and then I'll do problems as you have questions. That might be a better way of going about it. Um, so I'll tell you another thing is that when you go out in the real world and you're solving problems, they're not going to ask you textbook problems. Right? They're not going to be like, how far does this thing go? They're going to say, does this thing go 100 meters? You know, it's going to be like the airplane problem in the one-dimensional motion work. It's going to be, can the plane land? And you have to show that it can by some argument. So this is a common problem from the past. I don't know who plays football. I know that if there's one thing that's notoriously hard, it's kicking field goals in high school. So there's our goalpost in a helpful orange yellowish color. And we're going to have a person on the ground kicking. There's our person. And there are some requirements here. First off, to be successful, this thing has to have delta y is going to be 3.1 meters. The second thing is it has to actually travel the x direction distance. And here in our problem, we'll do delta x is 30 meters, which is just over 30 yards. It'll be like 33 yards or something. That's an NFL extra point, but I've seen people miss it in high school. And I don't think I could do it, so, Now, what we're going to do is have the person kick the football at a particular velocity and angle that we don't know if it's successful. So we don't actually know these numbers. This is just a goal. But we're going to set a velocity at an angle. And so ballpark, let's say 10 meters per second. And we'll put this angle in as 35 degrees. Now, there's some other stuff I should show you about calculating height and range. And I'll do that at another time, another video, but it's supplemental stuff. If you look in your textbook, there are probably height and range equations you can use. And the idea is that we can take our equations and we can manipulate them and find for a particular trajectory, the trajectory here will be, if I draw it in green, something that looks like that maybe. We don't know if that's it, but something that looks like that. This is just a parabola. This is just a graph that is y and x with some parabola in it. And so we can take an x point and find the corresponding y point, eliminating the time. Now, the reason I don't do that is that's complicated. You end up with a whole bunch of cosines and sines and tangents, and it's not necessary. It's not necessary unless you're trying to program a computer to do it without looking at the time. I am congested, and you don't hear me blowing my nose because I can pause the video. Isn't that wonderful? All right. So what we need is to organize our information, same way we did before. And we can ask a couple of questions. One, when delta x is 30 meters, is delta y 3.1 meters or larger? Or when delta y is equal to 3.1 meters, is delta x ever larger than 30 meters? All right, that's saying, is it good? But the idea is that we're going to analyze basically what happens, how long it takes it to go the 30 meters, and then where is it in height when it gets there? Or, vice versa, when it passes falling down through 3.1 meters, is it enough distance? And we can say 2, how long is it in the air? So we organize our information based on what we know. First off, some translatable stuff. Football occurs on Earth. We can assume acceleration. This is a projectile. This is free falling once we kick it. And so we'll have delta x is, maybe it's 30 meters, but we're going to leave it blank for the moment because we don't know. V initial x is going to be our velocity times cosine theta is 10 meters per second cosine 35 degrees. So we'll pull in our calculator, clear, 10 times, and then we find the cosine of 10 times cosine of 35 is 8.2 meters per second. V final x, we don't know. The acceleration in the x direction should be 0 because there's no air resistance in these problems. And the time we don't know. All right, so we do know what V final x is. V initial x. We don't know what V final y is. So let's go do. So delta y, well, we don't know what that is yet. We have an idea. We can check, but we're going to have to do this a couple of times, probably. And so we have V initial x is V sine theta. So it's 10 meters per second, sine 35 degrees. I'm going to guess it's about 6-ish. 10 times 35 sine. 5.74 meters per second. V final x, we don't know. The acceleration in the y direction, we know, is minus 9.8 meters per second squared, and the time is, we don't know yet. So what we can do is say, as we're trying to solve this problem, is say, when does it get to 30 meters? And then use that to say, is it in the right spot? So what we'll do is separately come in here and say, is it 30 meters? And then we'll find the time. And that we can deal with. Right, is that we have delta x is our velocity times delta t. All right. And we know the acceleration 0, so all our equations simplify to this form. And so we can put in that it's delta t is delta x over v is 30 meters over 8.2 meters a second. So delta t is going to be 30 divided by 8.2. We have 3.66, not 6. Why did I round the other way? Meters per second. Not meters per second, seconds. Let me rewrite this for clarity. 3.66 seconds. Now we can plug into this equation over here. Right, we have 3.66 seconds. Now we have some more information. We can ask what delta y is here. And we probably also want to know what V final y is. Or it might be a good idea to know, is it going up or is it coming down? Did we actually get where we think we're going here? And so we'll do delta y is V initial y t plus 1/2 ay t squared. And so we'll go and we'll say 5.74 meters per second times 3.66 seconds plus 1/2 9.8 meters per second squared negative times 3.66 seconds squared. Let me rewrite that. Oops, that was the last video. So we'll have delta y equals v initial y t plus 1/2 ay t squared is 5.74 meters per second times 3.66 seconds. And so you can see there's our information we're getting from there's v initial, there's our time, and then we're going to do plus 1/2 minus 9.8 meters per second squared and 3.66 seconds squared. And so we'll calculate each term separately. So 5.74 times 3.66 is 21 meters, 2.5 sig vigs, oddly, plus, and then we have 1 divided by 2 times 9.8 is negative, and we have times 3.66 squared, and it'll be minus 65.6 meters per, so 65.6 meters, and so it's negative. Right, delta y is 44.6 meters below the ground. So this is a miss. But we can ask, where does it hit the ground? How far does this kick actually travel? And that's a valid question. So we can ask, how long is it in the air when it hits the ground? And so that means we're going to have to rearrange our information, is that we no longer have the assumptions we had here. We've got new assumptions. And our new assumptions, all right, we're going to start out with is delta x is unknown, but delta y is 0 when it hits the ground. And then we can go back and figure out what delta x is. So what we want is delta t, and we want delta x. That's our goals. But now we can reuse the rest of this information. Velocities will be the same. So v initial x is 8.2 meters a second, and v initial y is 5.74 meters per second. V final over here, and acceleration is going to be 0. Ax is 0. So v final x, and in t, we don't know. But over here, v final y, we don't know. The acceleration in the y direction is minus 9.8. And t, we don't know. And so the idea is that from this, we have 3 things in this column. We ought to be able to find the time. And we need something that doesn't use v final. And that is delta x is v initial t plus 1/2 ay t squared. Or this is going to be delta y. And then we have vy initial and ay. So that's going to lead us to a quadratic. We could also find v final, but let's just go through the quadratic. All right, delta y is going to be 0. We're going to have v initial t is 5.74 meters per second times t. And we're going to have 1/2 minus 9.8 meters per second squared t squared. Now, I can tell you that this thing already has 2 solutions that are easy to get because we can factor out a common t. This is going to be 5.74 minus 4.9, when I simplify this, t, times t. We factor out the common t. So that means it has 2 solutions. T equals 0, or t is minus 5.74 meters per second divided by minus 4.9 meters per second squared. T equals 0 is understandable. That's the moment you kick the ball. It's on the ground. So that's the moment where, the motion begins. We expect that. This is what's called trivial. Right. This is the one that we actually care about. And when we calculate it, we get that this is 1.17 seconds. And now that lets us go back into this equation, find delta x. Right, so in red here, delta x is v delta t is 8.2 meters per second times 1.17 seconds is, take our number here, multiply by 8.2, 9.61 meters. This kicker kicked the football for a 33-yard field goal, 9 yards. And generally, if you've seen a high school football game, the line, the kick occurs 7 yards behind the line. So he basically kicked it to a linebacker. Right? This is not a good kicker at this moment. Something went wrong. But this is how you organize your information. Right? The idea is that you organize this stuff, and you have a big question: is the kick good or not? And to figure out if it's good, you ask, well, where is it when, say, you try it. Where is it when it travels that far? And you find out it's in the ground. It couldn't have gotten that far. And so you go back and you say, well, how far did it go? So you organize your information like this. There's other ways of organizing it. You could say, when does it hit the ground? And check that, yeah, it's too short. But, you could have a problem where it actually does make it and goes beyond. And so that's a good question. Where does it hit the ground over here when it's good? Right? So there's multiple ways of solving problems like this. All right, so that said, that's a good place to stop this video, and we'll do something else. If I can get the mouse over here to stop it. So